Good afternoon, sir.
Good afternoon, sir. Good afternoon, sir.
We'll start, sir, in 2 minutes, sir.
No
Just
issue.
wait
Is
for
my
the-
voice audible?
Yeah, it's audible, sir.
Is there any background noise?
Some howling is there.
Okay. Let me connect through Bluetooth.
Hi, Rahul sir. Namaste.
Namaste, sir.
Namaste.
Namaste,
Namaste.
sir.
I'm Dr. Sojanla, principal of the college. I attended few of your FDPs online.
Thank you very much, sir.
All exciting journey, sir. Thank you very much.
Looking to serve you all. Thank you.
Yeah, thank you, sir. Thank you very much.
Sir, can we start? You are muted, sir. Rahul, sir?
Yeah, you can start. You go ahead.
Okay.
Welcome
Please
back
go
all.
ahead.
Dr. Rahul Jaswantbhai Pandya is an associate professor in the Electrical, Electronics and Communication Engineering Department at the Indian Institute of Technology, Dharwad. He holds a BTech from Sardar Patel University, Gujarat, an MTech and PhD from IIT Delhi, and an MBA in Finance. He has also served as a Sire Fellow at Virginia Tech, USA. Prior to IIT Dharwad, he was an assistant professor at NIT Warangal and a senior network design engineer at Infinera Private Limited, Bangalore. His research interests span wireless communication, optical communication, computer networks, machine learning, and artificial intelligence, with a particular focus on 6G semantic communications and AI/ML-driven network design. We are honored to invite Dr. Rahul Jaswantbhai Pandya to deliver an online session on 6G semantic communications, a practical MLDL implementation framework at our faculty development program on advanced communication systems shaping next generation networks, organized by the Department of Electronics and Communication Engineering, Jyoti Engineering College, Cherudurthi. We warmly welcome your gracious online presence and valuable insights to our community. Welcome, sir.
Thank you very much, madam. Is my voice audible?
Yes, sir. Yes, sir. Very much.
Is there any background noise or?
No, it's fine.
Very clear.
Okay, then we can get started. I'm going to share my screen. Is that okay? Okay, sure. Thank you.
Sir, I'm also alumnus of NIT Warangal, 93 MTech Computer Science Fest.
Yeah, Jayesh Prakash, this KV
Jai Kumar.
Jayakumar sir, he said that to me. He informed me.
Yeah.
We were
Just
discussing
now while
about it.
introducing, it has reminded me again.
It's good to know. Good to know. And I also somehow I got the chance to serve NIT Warangal also. It's a great institution. It's very difficult to get there as a student, as a faculty.
Yeah, I know that. I know. So
There are too many. Actually, our ex-director is also a passed out student from NIT Warangal. Professor
mechanical.
P. Sheshu.
Sheshu.
Professor P. Sheshu. He
Yeah,
was also a student of NIT Warangal.
I think he was mechanical.
Yeah, he was mechanical. He's from mechanical.
Yeah,
Good to know, sir.
good to know, sir.
Well, let me know when my screen is visible.
Yes, sir.
All right. Firstly, thank you very much, Principal Sir, and your institute for inviting me on this occasion of your FDP, as well as I congratulate all the coordinators for organizing such a great FDP to share the knowledge with each other and other participants. In this session, we will discuss a little bit of core technical topic about the 6G semantic communication and the practical MLDL implementation framework. We'll begin with the theory, and in between 20 minutes, we'll have the hands-on exercise also. I'll demonstrate the code and simulation environment. Subsequently, I'll share the code also with all of you. You may take a look. Whenever you are free, you can establish the environment and you can give a try also. Let's begin with today's topic. What we are going to cover is, we'll begin with the conventional communication. Subsequently, we'll cover semantic communication. What are the differences between the conventional communication and semantic communication? What is the role of the knowledge graph or knowledge base in semantic communication, and how it differs from the conventional communication with reference to the semantic communication? Then we'll take a look at several methods such as deep learning algorithms or methodologies, what we use frequently in the communication systems. And we will also visit some of the research opportunities such as, let's say, machine learning, deep learning for semantic communication, trade-off between the quality of services, bandwidth, and semantic representations, neuro-symbolic AI, causal learning, and goal-oriented communication. We'll also take a look at one demonstration experimental framework where we'll take a look how to simulate the semantic communication. Let's begin with the basic concept of the conventional communication. The existing wireless systems, they work based on the Claude-Shannon's information theory, right? Claude-Shannon's information theory. And the goal was to transmit whatever the bit stream comes in, to transmit that entirely. And it's semantic agnostic, which means, let's say, if I receive any message at the input, I will convert that into the bit stream, the entire message, and then I'll transmit over a wireless communication channel. That's a traditional communication channel. And based on that, 1G to 5G were evolved. For the people, those who may be new, I'll just quickly explain the conventional communication system where, let's say, I got the bits. Using the source coding methodology, or you can say source encoder, we compress the message. Then we transmit to the channel encoder, which will add the redundancy methodology, such as, let's say, CRC or the forward error correction. Then it goes to the modulator, where we select the appropriate modulation, such as QAM, maybe 64 QAM. And then it is transmitted over a noisy channel, which adds the noise, maybe additive white Gaussian noise, interference, fading, distortion, the channel impairments. And could be with reference to 6G, could be the human blockages or molecular absorption or heavy path loss because of the higher frequencies. At the receiver side, we receive that signal, demodulate it. We undo the channel encoding using the channel decoder, which means we have the forward error correction and decoding, which will predict the errors and correct the errors also. Then we decompress the message using the source decoder. People use Huffman coding, or there are multiple coding methodologies available. And then we deliver the signal. Now, it is working fine, but the problem is it never considers the semantics part of the information. It's semantic agnostic. Now, semantic means the meaning behind the information. It doesn't care about the meaning of the information. Whatever the information comes in, it transmits. Now, if we understand the meaning of a particular information and make it goal-oriented, in that case, we can save huge amount of resources because we don't have to transmit the entire bit stream, which means we selectively transmit what is necessary, what is important. Else, we do not transmit that. So the motivation behind to adopt the semantic communication is to maximize the data rate, because going forward, we have the complex applications and we need high data rate to support. Furthermore, we are going for the higher frequencies where we might be facing higher blocking, atmospheric absorption, propagation losses, and a lot more other things. To avoid all this, we have to be very careful when what we transmit, so that we can unload the channel with higher data. So that's why we look for the alternatives, and we found out this alternative that could be a semantic communication. In semantic communication, on top of the conventional communication channel, the entire semantic layer has been added. So what it does is, whenever I have a message from the source, my semantic encoder or the transmitter will have one kind of knowledge base, and in that it will try to interpret the information and extract the meaning behind that. Such as, let's say, if I am a student and if I'm going to attend an exam, rather than memorizing the entire answer to a particular question, I'll try to understand the methodology or approach. I'll try to understand few important points, few equations, maybe few values, and then I'll try to make out the entire answer creatively in the exam, right? So that is analogous to this. Whenever I have an information coming from the source, I try to extract the meaning behind the information, and then that selective meaning of the information can be transmitted over this black box channel. The selective meaning of the information can be transmitted over this black box channel, right? So this is called the semantic communication. For that, we need a knowledge base between the transmitter and receiver, should be same. So for an example, that could be a trade-off also. Let's say if the knowledge base is rich, we don't have to convey much to the receiver. It understands easily. If the knowledge base is evolving or developing, we have to transmit more to train the receiver. It is analogous to the first year student. When a new student comes in, we have to train him with more rigorous detail. When he goes to the final year, he understands it very easily. We don't have to pass on that much of detail to him, right? So that is also analogous to this particular semantic communication, right? So these are the three levels of semantic communication that which we discussed. Now, the entire workflow, how it works, if you want to take a look with reference to the advanced wireless communication system. So what we do is, let's say we have the input data, such as, let's say, text, images, video, or sensor data. We perform the semantic extractions first. How we perform the semantic extractions? We can apply maybe, let's say, self-attention based algorithm, which extracts the information's meaning rather than transmitting the entire information. And once those semantic representations are extracted, it goes to the channel encoder and it performs whatever it is performing, including these, source encoder will do the compression, channel encoder will do the error for corrections and other things, forward error correction and other CRC kind of method. Then it goes to the modulator, where we use this kind of modulation schemes, and then it goes to the wireless communication channel and receive it. And these are the applications. These are the applications what we receive, right? These are the applications what we receive. It is widely useful across these advanced applications where high data rate has to be transmitted. And the goal of the semantic communication is to solely provide the meaning of the message rather than transmitting the entire message. When we transmit the meaning of the selective message, it loads lesser on the system, on the wireless system. So we can save a lot of bandwidth, we can save a lot of energy. Now, here the meaning is essential. It has to be extracted. Now, how do we extract the meaning is, for that we have to develop a knowledge base. Here we say that we have to develop a knowledge base, right? This knowledge base. How we do that? There are certain ways to develop the knowledge base. One important one is important technology to develop the knowledge base is called logic tensor networks. Using that, we develop the knowledge base, symbolic knowledge base. There are certain traditional methods also, which we'll discuss soon, based on the probabilistic rules, right? And once we have developed that knowledge base, based on this SNR, signal to noise ratios information, we can do the trade-off between how many semantics we transmit and how many we keep, right? This is often called goal-oriented communication also. This is often called goal-oriented communication also. And the main aim for the semantic encoder is to detect or extract the meaning of the information. How we do that? So there are several methods. Let's say if we employ the classical methods, they would be based on some sort of logical rules and probabilistic equations. And using that, they will quantify the meaning behind the information. And they'll be presented, the meaning would be presented in the form of the logical probabilities and truth values. Developing the knowledge graph in which present the entire information in the form of a knowledge graph. You might have heard about the mind maps, right? So this is analogous to this. We can employ machine learning and deep learning algorithms also there, such as, let's say, advanced logic tensor networks or neurosymbolic AI or maybe deep neural networks based technology to extract the meaning and present the meaning, right? There are certain other ways also, let's say, significance data point based method where meaning is represented by the significant information points. So these are the methods that we use to extract the meaning or the major intent behind the information. So we do not transmit everything, but what we do is we transmit the major intent behind the information only. And we try to save a lot of bandwidth. And since we don't transmit much, we save huge amount of energy and latency also. How this knowledge graph works? So this is one knowledge graph of a particular information, how we build this. So let's say for an example, we are discussing about Albert Einstein, and the major points, he has written a book on theory of relative, and he got the Nobel Prize, and let's say he studied from University of Zurich. Now these are the major things, right? So what we do is we break this entire. So you got the paragraph, I got the paragraph. Let's say the Einstein was a great scientist. He published a book on theory of relativity. He accomplished a Nobel Prize in so and so year. He graduated from University of Zurich, Germany, right? This entire paragraph, and he was a physicist, right? So this entire paragraph is captured in the form of a mind gap. And what it does is, for each, it creates the entity, relation, and entity. So for an example, here you can see the first entity is Albert Einstein. This is how it is coded. Then the second entity is the book of theory of relativity. And what is the relationship between entity 1 and entity 2? That entity 1 is the author of the entity 2, right? And then we got this encoded array. Now this can be quantified using probabilistic rules or maybe logic tensor networks, and it can be grounded to the number. So you get the number, right? And this is how one information is encoded here. Now, similarly, you can have different information such as, let's say, first entity is Albert Einstein, second entity is University of Zurich, and how are they related? That Albert Einstein has graduated from University of Zurich. So this is my second message, right? So you can see this is my first message, which is encoded. Here you can see this is my entity E1. This is my entity E2. This is my entity E3. sorry, this is my entity E2 and this is the relationship between them. This is the relationship between them, right? So here you can say R1, relationship between them, right? So that's how they are related and that's how they are related. And using that information, I can transmit the message in a crisp format rather than transmitting the entire bit stream of my message, what is incoming, right? So now here you can see one more example. Here you can see one more example. Here you can see one more example. Let's say another example which I want to transmit. So my transmitter received this particular text that, let's say, Steve Jobs is a graduate of the Reeds College and he founded the Apple. Now, the beauty of the semantic communication is we don't have to maintain the entire structure of the information. We can shuffle it up, right? The only thing is we have to understand the meaning behind of the information and then reproduce it. Let's say, for an example, I'm preparing for the exam, right? And I'm trying to remember a particular answer for an exam. So what I do is I try to extract the semantic and I try to construct this particular graph. I try to construct this particular graph. So you can see I've constructed this graph. This is called my knowledge graph. Right? So you can say this is my entity 1, E1. This is my entity 2, E2. So you can say Steve Jobs has founded the organization called Apple. So he's the founder. Right? Now I put this message on a traditional wireless communication channel and I receive it. Now let's say at the receiver side, I receive this particular, if the channel condition is good, I receive this whole 2 segments. So you can say Steve Jobs is the first entity, second entity is Reeds College and graduate. And these are, let's say, you can have the numbers, right? You can, let's say, after some sort of probabilistic logic, you have some sort of numbers. So this is how you get the array, correct? And then using that, you can easily understand. Now, based on that, I can reconstruct my message and say, Steve Jobs graduated from the Reeds College and he is the founder of the Apple, right? So this is the best case, but you can see the structure has been changed a little bit. It's not exactly what I've received, but that is okay. So let's say I'm not expected to write the exactly word to word answer in the exam. I'm okay if I can reproduce the major concept and approach. The examiners will understand that, right? Examiners will understand that. So same concept and analogy we apply here and we try to do that. Now let's say the channel condition is not good, right? This was a good channel condition, right? Good channel condition. You can say this is a good channel condition. And if the channel condition is not good, right? If the channel condition is not good, so which means what I do is I do not receive the whole information. I just receive few entities because the channel will impact and some of the entities and message segments are lost. But still, I am able to receive this particular segment of information and then I could reconstruct this entire message. So if I side by side compare, this is the case of good channel condition. This is a case of good channel condition. Which means, let's say the noise is less, right? So I receive everything. The knowledge graph is also good. Let's say knowledge graph is also good. Knowledge is also rich across the transmitter and receiver. So they can understand what has been transmitted. Now let's say channel is not good. What's channel condition? Not good. I'll just say not good. Right? Still I could recover from the selected segments which I have received. Right? So now whereas in traditional communication, what it does, it will totally fail and say, okay, I'm not receiving what has been transmitted exactly, you retransmit. Right? So that is something unacceptable when we have mission critical services. We cannot tolerate that kind of delay or multiple retransmissions. Now, if you look at this, the same example with reference to the images also. There are, let's say, if I'm transmitting multiple images and I convert them into the bit stream and then I transmit and I receive. Now there could be some sort of errors in between which I have to correct and have to receive. If I receive it, it is good. Otherwise, it's difficult. But instead of this, what I can do is I can transmit the major meaning behind the information, the image, right? And using some sort of, let's say, generative AI algorithm, you can say CGAN, right? CGAN, or maybe diffusion algorithms. You can reconstruct the images using this generative AI algorithms easily. So we don't have to load channel this much. we can extract the major meaning behind the information and then transmit it. Let's say security applications, right? Surveillance applications, where we don't have to have the high resolution video, but we have to look at the major meaning behind of the information. That is there anyone trying to enter the premises, right? Unauthorized entries or restricted area is been accessed by unauthorized personnel. In that particular case, you can easily transmit this capture through the PTZ cameras and transmit that and then say, okay, unauthorized access to the particular area. So that's how we can do that. So such as, let's say a person is riding the horse, let's say entirely transmitting this, what I can do is extract just the semantics and transmit it, right? So I just received that at the here. I don't have a tab here. So I just received that here, right? So that's how I can do that. That's how I can do that. Now, there could be some sort of errors. Let's say the difference between the conventional communication and semantic communication is there could be some sort of errors here. So let's say that if I'm transmitting conventionally a particular message, let's say Bob automobile was parked here. And if there are some errors, in that case, entire message will be rejected because few bits are flipped and they are in error, and maybe you can see it's not been passed. Whereas in the semantic communication, we don't care about the exact bit stream or the exact information. Let's say if the transmitted message is Bob's automobile was parked here, even though there are errors, if I am receiving something nearby, let's say Bob's car was parked here, I can still accept that message and says it talks about the automobile and parking, right? So that's how we can avoid the retransmissions on the system and save huge amount of bandwidth. Right? So now let's take a look at okay, I just skipped through some of the slides. Yeah. Let's take a look at some of the MLDL methods for the semantic communication, which we will use in the code demo. So let's say now these days, the encoding, source encoding, channel encoding, semantic extractions, resource allocation, everything is preferably done by machine learning and deep learning. And the advantages is we apply that also for the semantic communication too. And the advantages are we don't need the complex mathematical model to be running live on the system. It can be offsetted to these deep learning models and can be a little bit of lighter, right? So machine learning based communication systems. It can be used across any layer. It could be used as a source coding, could be used as a channel coding, could be used as a semantic extractions, could be used for resource allocation, could be used for channel estimation, could be used for channel modeling, right? So it is everywhere and it's good to use them. The advantage is what we receive from the deep learning is it enables the lighter model without the need of being complexly mathematically modeled, and entire the representation representation extractions or feature absorptions can be done automatically. Now, what do I mean by the representation extractions or feature expression absorptions? Which I'll explain in next couple of slides very easily. We'll understand that what it means. And the channel is how do we define the meaning behind the bit sequences? That's the major challenge here behind the semantic communication. How do we define or extract the meaning behind the bit sequences? And what are the different matrix, the performance matrix that we'll use it, right? Such as, let's say, ROC score or maybe BLEU score, semantic similarity, cosine similarity, many more others that we'll look into that. How to design the system at a semantic level. So now if I look at this has been integrated across several layers. Even we can apply, let's say, self-attention based transformers to extract the meaning. And then you can use a deep learning based neural networks to establish the knowledge graph. And using that, in fact, that's what these language models are doing these days. When we interact with any of the large language model, right? Large language model, it can be used to develop the encoder, semantic encoder, channel encoder, source encoder. It can be used to maintain the knowledge bases. It can be used to maintain the channel. It is applied everywhere. Now, how do we do this? Practically, let's say if I have any image or a video or a message, it could be multi-modal data, right? The text, images, or a video. So for an example, let's take an example of an image. This image I have to transfer. So this is my semantic space. What I do is using this kind of semantic extraction, I extract the semantic label of the information. So this is my semantic label of the information. You can see it explains the major meaning behind that. This is the car here. This is the car parked here. That's the car parked here. So the cars are running over a road, right? Mostly this is applicable or useful for autonomous driving application. Right? So let's say if I'm taking a reverse gear in my car, there would be some sort of screen, and on that particular screen, I might be able to get that capture as well as what you call the sensors that can produce the voice based on this received images that I have to drive slowly or something like that using the sensors and other things. Then it goes to the channel encoder, then decoder, and then there is a semantic graph, right? Semantic graph understands, it has a shared knowledge. It has a shared knowledge that it will understand that, okay, this has been transmitted here. And it talks about some sort of driving, and I have to take the decision based on that image, that okay, or image, because video is a sequence of images, right? Video is a sequence of images or a sequence of frames. So t is equals to 0 to t is equals to n. T is equals to n. So using that particular image, what I can do is I can take a decision on my driving. I can immediately stop, or it could be automated driving also, right? So accidents can be avoided. So that is adding the safety margin. That is enabling safety margin, right? So now how do we do this? In the semantic space, let's say this is my original image. This is my original image. And this is my received image. Right? And what I try to do is I try to minimize this distance between them. So I try to minimize the distance between them. That is helping me to increase the semantic similarity. That is helping me to increase the semantic similarity. I try to minimize the distance between them. That helps me to increase the semantic similarity. Right? That helps me to increase the semantic similarity. Same thing is applicable for the multi-modal data also. Same thing is applicable for the multi-modal data also, such as, let's say, for human speech. Let's say for human speech, or maybe music song, or maybe natural sounds, where I can convert them, extract the major meaning behind this, and I can do that, right? So that is applicable for the huge speech applications also. Semantic communication is applicable for the speech applications also. There are certain research opportunities in that, such as, let's say, there is a huge scope of developing new MLDM algorithms for semantic communication, which includes the generative AI, or maybe advanced generative AI, or maybe advanced natural language processing based methodologies, which we have to apply. We can develop some sort of algorithms and experimental design to handle the trade-off between the semantic representations, quality of services, and the bandwidth trade-off. We can have some sort of, let's say, LTN, logic tensor based research opportunities, causal learning based research. So this is one hot area, hot research area, causal learning, right? Hot topic for semantic communication. Whole field, such as, let's say, goal-oriented communication, or some people, they call it intent-based communication. Some people say intent-based communication, right? So let's take a look at one common parameter, what we use, performance metric. Generally, what we use is we use the semantic similarity as a performance metric. Semantic similarity is, let's say, in the semantic space, if this is my original information and this is my received information, right? I try to minimize the difference between them. So if this is, let's say, 0, which means there is a huge difference between them, which means they are not related, what I am receiving or what I am transmitting. But if this is 1, right? So let's say both the information are nearby. 1 means, let's say, they are nearby. They are exactly the same, but I'm trying to put them closer. So maybe you can say semantic similarity is, let's say, 0.9, right? 0.9. So this is not volt. Some of the people will get confused, right? So this is called a degree of similarity. So what it does is we convert the text into the vectors, and then we transmit, and then we measure the semantic similarity or cosine similarity. If the similarity is large, we say that all in all, the information what has been received, that is really good. That is really good. Now, since we have talked 30 minutes about the theory, let's take a look at the code. In between, if you have any questions, please feel free to stop and have a discussion rather than having a monologue, right? In between, if you have any questions, please feel free to stop anytime rather than having a monologue. I'll give you 1 or 2 minutes. If you have any questions, we can discuss. In the meantime, I'll set up the code environment.
Okay, sir, I have a question.
Go ahead.
Okay. I'm concerned about the privacy of the communication in case of semantic communication. Can you comment on that?
Your concern is about the priority of the
Privacy.
privacy. Yeah, privacy, we use that special, See, privacy is really the issue these days. So there is a whole cybersecurity kind of thing, right? So see, whatever the information I use, you can use SHA 256 encoding algorithm to create the ciphers of my information, and then we transmit. And we can use the blockchain technology also. I'm writing on the computer screen, so that's why handwritings are not good. Using the mouse, I'm writing. Right? So you can use the blockchain technology. So these two are sufficient to maintain the privacy of this. If you want to increase the further security and privacy level, there is a whole branch for it. So there are multiple generative AI-based algorithms which will improve the security. So that's really a concern these days. Specifically, let's say the application called defense. Right? So that's where it has to create a difference. But that's a good question.
Thank you, sir.
You're welcome, madam. So I'm setting up one code demo. So generally the theory is boring always. So a little bit of theory in between, a little bit of code we'll do, and then we'll try to understand this. Right. So let me just bring it in. Okay, so this is one code which I have created to demonstrate this today's concept. What we have, I'll just explain the what you call this one first. Let me have. Okay. So see, this is the today's code demo, right? This is block diagram. So we'll discuss one by one. So this explains the semantic communication. So all in all, what I have to do is my semantic communications basic was what I was doing here is, right? So here you can see first we'll define all the blocks. So this is my information stream. In the coding, what we'll do first, we'll define the information, how to extract it. Then semantic block, how to extract all the information, maybe using the self-attention based transformer. Then we'll define the source encoder block. Then we'll define the channel encoder block. Then subsequently, we'll establish the modulator block. Then we have a wireless channel. Then we have a demodulator. Then we have a channel decoder and the source decoder and the estimator, right? So this is some sort of overview of my code. So now let's see, this is the detailed block diagram of my code, which we will discuss now. Where is it? Yeah, here it is. So let's say if I get my information from anywhere, that could be the source, could be text, speech, image, video, sensor data, anything. Once I receive this, what I have to do first is I have to do the digitization, or maybe if it is, let's say, text-based information, I have to do the tokenizer, or you can use the parser. If it is images or video, we have to use vision transformer and then convert them, or maybe CNNs, and convert them in terms of matrix, quantify that, and then transmit, right? Let's say tokenize, for an example, let's say a message, hi, how are you? So I use a tokenizer, which will tokenize it or parse it, right? So that's my first block I have to define in the code. So see, let's say I'll install all the packages. So you can, this is a Python code. You can definitely install all the packages. And this is my NumPy configuration. I'm using that PyTorch, that thing. The first thing is when I receive any information, I have to first tokenize it. So I'm using that bar tokenizer here. So you can see that it will tokenize. Let me zoom it so it will be easier for you to see. So I'll use the bar tokenizer. So it will tokenize what we have. So here, this is the first block. So I'm trying to put it in parallel, a block and its code, so that now we don't just discuss the theory, but we try to understand the simulation also. Once we do that simulation, we can do experiment on software-defined radios if we have hardware in the lab, right? But mostly if we don't have hardware in the lab, still we can do the simulations and we can satisfy our curiosity. So I'll do the tokenizing. Once I have once I have tokenized output, right? So whatever the information, let's say a message I have, I call the tokenizer, bar tokenizer. That's an inbuilt model which we can use it. You want to understand how it tokenizes further. There are certain ways to do that, such as, let's say, text to what do you call vector conversion library and other things, how they work. They might work on different algorithms, such as, let's say, hot encoding. How do we do the tokenizing? You want me to explain that? I'll just quickly explain you. Let's say hot encoding, or one hot, what do you call, one hot encoding or something like that, right? So let's say hi, how are you, right? So there are 4 words here, so I'll use 4 bits, 0, 0, 0, 0, 0, right? So that's my initial position. And then for a hi, I'll say, okay, 0, 0, 0, 0, 0. That's my first word, right? So sentence is hi. Then how means 0, 1, 0, 0. R means 0, 0, 1, 0. U means 0, 0, 0, 1. Right? So sentence is, let's say, hi, how are you? Correct? Which would be transmitted as a vector like this. 1, 0, 0, 0. This is called tokenizing. Right? People will have question. So what is tokenizing? So then we'll transmit in this way. 0, 0, 1, 0. This is a simple method, and there are advanced methods available. This doesn't work when we have, let's say, thousands of paragraphs or sentences or words, or maybe it fails. But at the time we have the advanced one, but you can understand the concept, right? So this is the entire vector of the message which we transmit. This is called the tokenizing. This is called tokenizing. Right? This is called tokenizing, right? So if you are unable to understand, let me just put a blank page so that you'll understand it very easily, right? So see, here you can see my message. This is my message. We have tokenized it, and I transmit this now, correct? I transmit this now. So I just clear the drawings now and then go back to my code now. Okay, so so that's what we have done here, tokenizer, or using parsing or tokenizing method. That's what we have done. Once we have done this, I have to extract the semantics behind this. So mostly we can use the self-attention based mechanism here. Now this is the second block, self-attention based mechanism. So what I do is I'll try to call, yeah, let's go upside. I try to call this self-attention based encoder, or maybe you can use the BART, that one also, to extract the semantics, right? So here you can see I'm trying to call this particular self-attention based mechanism or BART encoder, right? So to extract the semantics. So model encoder. Encoder is already defined somewhere. Let me see. Yeah, should be defined. Yeah, here it is. Right, so this is semantic encoder, semantic decoder. So you can see this encoder is similar to this. It might be somewhere here. We can see BART-based encoder decoder has been defined. You can use self-attention based transformer also, right? Self-attention based transformer also. That is also good. Once we have done that, so now this is the semantic part. So we have extracted the meaning. Now we go into the black box, the channel, the wireless channel. So before that, what we do is first, let's say we apply the Huffman code to compress the information, right? We can use some sort of advanced methodologies also. So Huffman code, everybody knows that. So this entire block defines the Huffman coding. Now I can't explain each and every line, but I'll share the code. So you can take a look how that works. So here you can see that Huffman coding is that entire block does the Huffman coding. So this particular block has been addressed. Once the source coding is done, we enter the channel coding block. In channel coding, we apply the CRC or forward error correction detection mechanisms, right? So here we have model this convolutional encoding, which will add redundant bits for error detection and correction, right? So that block is well known. So these are the functions calling routines, which routines, which I'm going to call routines, which I'm going to call, right? And subsequently, what I can do is I can go and do the modulation. You can pick up 128 QAM, 64 QAM, or maybe OFDM or of your choice, whatever you want, right? So I've modeled 64 QAM here. You can see this does the 64 QAM modulation. This piece of code does the 64 QAM modulation. This is kind of, you can say the bit stream is modulated by 6 bits. So you can say 2 power 6 is 2 power 6 is 64 QAM. 2 power 6 is 64 QAM, right? So that's what it does here. Once it is on 64 QAM, the signal is further propagated on the wireless channel. The wireless channel is modulated as a relay fading channel plus AWGN, additive white Gaussian noise. You can have Nakagami fading also, Vision also. There are different functions available. These days, developing the code is not that much difficult. You can take assistance of Claude and you can have the baseline function. Only thing is you have to understand it nicely, change it as per your application and integrate it. So this is my wireless channel. You can say we are modeling it as relay plus AWGN channel, relay fading plus additive white Gaussian noise, which takes care about the fading, noise, interferences, and other things. So let's say I give the input to the channel, and then I receive the signal, the noisy signal, right? After that, I receive the noisy signal. So faded symbol comes from the relay fading, and the noise, which is AWGN, additive white Gaussian noise. So noise function is this, which adds the additive white Gaussian noise, and noise variance is defined through this. And you can say the faded symbol, H is the channel coefficient, and channel is defined through the relay fading channel. This is the equation which defines the channel, like the classical channel modeling equations. And then after that, what we do is we feed the information here on this particular block, propagate it, make it noisy, and receive it back. Right, so this particular part is been addressed here. For equalizing, we use the zero forcing receiver, right? That is used for equalizing. So you can see I'm using the zero forcing equalizer for receiving the signals. And since we have modulated using 64 QAM, I have to demodulate using 64 QAM. Since we have used for 64 QAM, I have to use demodulator for the same. So this demodulates the signal. So now we are here. You can see somewhere we have demodulated. At the decoder side, I'm using a Viterbi decoder, right? Just to prevent the errors, just to detect and correct the errors. I'm using Viterbi decoder. You can go through much in detail Viterbi decoder. There would be an entire book on that entire decoder, or you can use your other custom decoders or of your choice. Once that is there we have to do the bits decompression, right? See, we are doing the source compression 100% because we do the semantic compression at the, so let's say this is how it works. We do the semantic extractions here and we compress in the semantic domain, right? So this is called semantic extractions here. Semantic compression. You can call it semantic compression. Also, what we do is we do the bit level compression here, right, at a source. This is called the compression, traditional compression, bits compression. That we do definitely on top of it what we get from the semantics. So we have to undo this first. So that's why we apply that that thing and then we can restore back, right? So then we can restore back. So here I'm using this particular thing here to decode that Huffman decoding, right? Huffman decoding to decompress the signal. Now see, once this is done, what I have to do is I have to, the major part, I have to decode the signal through semantics. So as we have seen here, say, let's say now I've received this semantic, any of the semantics, right? So let's say I've received this. So I have to decode the semantic and generate the image, right? So you can use, let's say, CGAN, which will decode the semantics and create the image, right? Just like AI tools, what we are seeing these days today is that if I upload my image, it will create some sort of fancy image from my image only, right? So I train that and then subsequently it creates my own image. So that's how, so semantic decoder, you can use any of that, CGAN or diffusion or maybe BART or maybe self-attention, right? Anything you can use here. So this is my function which decodes that, right? So once we have it, it will generate the decoded output from the semantics and generate the image now and generates the image, right? So now see, these are the all blocks. We have defined all the blocks. Here you can take a look. We have defined all the blocks in the code. I'll share the code, right? I'll share the code. You can take a look at your own. You can run it or change it. See, we have defined this nicely. This is called tokenizer. Then we have semantic encoder. We have defined this in the code. See, all those codes we have defined as the function. Some of the people, they have always a question, how do we study the wireless communication? So if we don't have a hardware setup, we write the Python code. Avoid writing the MATLAB code these days. Python is better than MATLAB because we have these deep learning libraries integrated in that Python. Then you have the semantic extractions. Once we have semantic latent space, we have defined the Huffman code, which is for source compression. Then we have defined channel coding for adding the redundancies to avoid the bit. Then we have what you call modulator. Then we have defined the channel also, right? Then we have an equalizer. Then we have a demodulator. And then we have a channel decoder, source decoder. See, these all are the functions, right? So you can see all these functions, let's say number 1, number 2, and so on up to number n. So n number of functions are defined here. All n number of functions are defined here, right? Once those functions are defined, what you can do is you can build the main routine. So these all are the functions. So you can say steps means they are the functions. I'll quickly recap. Step number 1 is the function number 1 for semantic encoding. Step number 2 is the Huffman encoding. Then step number 3 is the convolutional encoding. Then step number 4 is the QAM modulation. It looks boring, but for those who are specifically doing the research work, it would be very much interesting because they have to be specific and discrete and go much more in detail, right? So theory may bore them. So that's why I thought of covering a bit of code so that people have an idea that how to do that. Once they have the curiosity satisfied, they can do it at their own. Then we have a box for wireless communication, then the function for receiver side, equalizer, then QAM, then convolution decoder, then Huffman decoder, then channel decoder. And once all the functions are defined, you have to do the main routine, right? From that, we call all the functions. So you define your Python environment, right? So I can't explain each line because it would be too much, but I'll share the code. And then the parameters what you want, so such as let's say blue score or a rogue score, they generally measures the semantic similarity. Semantic similarity. What it does, let's say semantic similarity. So for example, let's say if I'm transmitting somewhere here, let's say this is my transmitted information, and this is my received information. What is the distance between them, right? So that has been covered up by this kind of score. So if the score is, let's say, nearby this 1, which means it is really good. If the score is, let's say, nearby 0, which means I have to retransmit. Retransmit. Not good. If the score is 0, not good, right? So that's how we do it. See the calculation of the rogue score, there is a formula for rogue score which is called rogue 1, rogue 2, rogue 3. Rogue 1 is kind of a word level comparing. Each word is compared. Rogue 2 is kind of 2 words are combined together and then compared with others, right? Then if you have rogue 3, that means 3 words are combined together and compared the similarity. So it compares the paragraph. So let's say if I'm transmitting the entire paragraph, correct? Hi, how are you? My name is so and so, and I'm transmitting this entire paragraph. At the receiver side, I receive the entire paragraph and I try to compare them and try to measure the similarity that if I receive, this is receiver side, let's say, you can have a different color. Not sure color, can I change? Yeah, I can change the color. So let's say if the receiver side, this is transmitter side, this is the receiver side. If they are similar, my rogue score would be near to 1, else would be near to 0, right? And this would be larger rogue score, let's say rogue n, rogue n, which compares larger number of words in the paragraph. So entire paragraph. Rogue 1 means just one word is compared. Word comparison. When you increase more number of elements, it would compare the entire paragraph. Once that is done, transmitter side, see, start calling it, right? So you have received the information. Let's say this is your information. Okay. So I've just modeled here. This is the input. You can have video also. You can put the video. I've just taken a text. So you can have any text. Text, you can import the data set through the Excel sheet. Okay. Create an Excel sheet, whatever you want to transmit and put it here. Create a video file, whatever you want to transmit and read here. Right. So I'll just take that. Once you have this input here, I'm not transmitting directly. What I'm trying to do is I'm trying to put it through the semantic encoder and extract the meaning. Remember, semantic encoder we have defined, it goes to that particular function here, and then it will extract the meaning behind the information. And then it returns the meaning. Right? So same thing what we do. We read, we retain the meaning, and then we go to the exam and as a student. Yeah, we means as a student, all our faculties here. But let's say if I'm a student, if I go in that way, and I try to recreate the information there, where we last slide. Yeah, here, there it is. So here you can see that I can extract the meaning and transmit. Once I have that, I do the Huffman coding. I call the Huffman code block, which does the source coding. Then I'll call the channel coding block, which does the channel coding. Once that is done, the next block was QAM. So I do the modulation here. I call that function. So you can take a look here. I'm calling the functions step by step, one by one. I'm calling the functions step by step, one by one. So yeah, now I see I called this. I called modulator. Now I'm calling modulator. Okay, I'm here. I'm calling modulator. Now I'm here. Now let's propagate on the channel. So I'll call the wireless propagation channel. Right. So this is my channel. You can see I'll transmit. So I'll call wireless communication channel. I'll give my channel coefficient and channel similar to the channel here. It will give the output of the received signal and the channel coefficient and other things. This is my QAM, right? Signal to noise ratio you can mention again, let it go automatically also. Right, so I've done here so far, and now what I'm doing is I'm going to receive the signal. I'm going to apply the zero forcing receiver. So this I am calling, this block I'm calling now. Okay, receiver, yeah, this block I'm calling now. Once that is done, I'm going to call Viterbi demodulate, and then Viterbi decoder, right? So I'll do the demodulations. I'm calling this particular block. Then I'll apply the Viterbi decoder. Once that is done, once the bits are decoded, I don't have to do much. Everything is ready. What is it? Can I not clear this? Delete, yeah. So once I have decoded, I don't have to do much. Finally, I'll print my recovered text or video or whatever. Let's say if there is a video you play it, will show on the screen, right? If you have an image, you can display on the image, and then I'll see that, right? So whatever is coming out, and at the output side, I'll print it. It might take a couple of minutes or maybe a few minutes to run this. I've already ran through it. So you can see these are the couple of texts which have been transmitted and received. So here you can see this is the, okay, so this particular message you can see specifically. Then let's say wireless communication enables seamless data transfer without the physical connection. So this is exactly received. All the words are received in order. So successful transmission, right? It's able to recover. Now here you can see this has altered the text a little bit, but still the meaning is retained. You can see the quantum computing has the potential to revolutionize the complex problem solving. And whereas here you can see quants has the potential, right? So here you can see some of the words are altered, but still it can make the meaning out of this. Here you can see the final results. Rogue score is, let's say, 0.84. Blue score and rogue score is around 0.84, 0.85, right? Here you can see this. Sometimes it is 0.88 is also okay. Row L, that means says, let's say, larger paragraphs, they are retaining meaning correctly without any issue, and it's really doing well. So that's the coding. Now see, you can fancify this code, and then you can have the graphs of your choice, and you can write the research paper also, right? So those kind of things are done very easily, and you can use Claude to take help in coding if you are unaware of all those things. Any questions so far? And then last 30 minutes, we'll wrap it up. Feel free to interrupt in between anytime if you have any questions. Now let's take a look at some of the research opportunities in semantic communication, right? Let's take a look at some of the research opportunities in semantic communication. So there is a trade-off between the semantic representations, quality of services, and the bandwidth. See, the transmission of the increased number of semantic representations, sometimes what it does, it broadens the bandwidth. So let's say, for an example, it's difficult to understand. I'll explain you in a different way. Let's say you've got first year student in your class. So what I have to do is I have to explain him everything is nicely, right? Or maybe you can take, let's say, rather than the student, or maybe I can take an example of, let's say, my I got two sons, right? So one son maybe 7 years old, and 8 years old, and one son is 3 years old. So if I have to explain the same situation, same message to both the sons, right? I have to explain more and spend more and more time with my younger one. It takes me, let's say, 20 minutes to convince him for something. Whereas it takes only 5 minutes to convince my older son, because he's a little bit of older and his knowledge base has been developed. So same ways, let's say if I got first year student, I have to teach him very rigorously, very much detail. But if I got a final year student, I don't have to teach him much. He will understand the basics easily. Knowledge graph is rich. So there is a trade-off, right? So how much semantic I can transfer and how much semantic I can save. So let's say if I am transmitting too much, which means it's going to take a lot of time, right? 20 minutes to explain my younger one. Let's say it takes a lot of bandwidth to transmit those kind of premature receivers. It won't receive it. So the bandwidth and energy consumption goes up. Whereas, let's say if the knowledge graph is established nicely, channel conditions are good, I can reduce the number of semantics. I can deliver the same quality of service at a lesser bandwidth consumption and energy consumption. Therefore, there is a trade-off between the number of semantics transmitted, quality of service, and bandwidth. And there is nothing right and wrong. We have to adjust according to the situation, and then we have to do that. I cannot complain that I have to explain too much to the first year students and lesser to the final year students, because that's both the situations are different, and that's a job. We have to adapt according to that particular situation. So optimal number of semantic representations, how to extract that to conserve the bandwidth and energy. That's one research problem. There are a whole lot of research works are going on that particular direction for the adaptability in the semantic representations. We can apply neurosymbolic based adaptations, probabilistic rules based adaptations, fuzzy logic based adaptations, and then we can have the optimization problems designed. There's another problem which people are working on is called disentanglement of the memorizable data and learnable data, right? So let's say classical communication will definitely transmits everything, whatever comes in, whereas semantic communication transmits only the selective things. One important difference in the semantic communication is, let's say sometimes some of the information is very much memorable, right? So we don't have to do anything. Let's say if I'm driving from my home to the office, very much I don't have to do anything. I can drive maybe in 5 minutes, and then maybe 10 minutes, maybe 20 minutes, and just reach home, reach office or come back. Right? Route is fixed, memorizable data. Route is fixed. Nothing much has to be done. Just go and execute. Right? So again, we don't have to transmit much of the semantic representations there. But let's say if I'm traveling on maybe an unknown route, then I might have to navigate through the GPS. I might have to stop by to a particular village and then ask people about the route. It takes much more time and representation. Same way, let's say information is complex. In that particular case, it's not memorizable, right? So those kind of things can be addressed differently, and we can transmit more number of semantics. So that's how we can do that. One more advanced research problem which people and researchers are working is called causal learning. In causal learning, you can see it's called neurosymbolic based causal learning. Sequential. Sequential, that means one action leads to the subsequent action. One action leads to the subsequent action, and what are the actions and reactions? And according to that, it interprets the message, extracts the semantics using maybe GFlowNet or other advanced methodology, and then tries to do that. So this is some sort of hot favorite research topic what people are working. Some of the researchers, they are working on this particular this particular topic. Some of the researchers, they are working on this particular topic. You can find out more number of papers here. This was from the archive, but now I think that author's paper has been published in one of the IEEE transaction journals, so you can take a look there. Goal-oriented communication. This is extremely important in very much mission critical services, where we just focus on the major intent of the information and get rid of it in the least possible latency. It's a specific goal that we focus. What is the major intent behind this information, and what is most relevant, which has to be sent, right? So that will help us to optimize the performance. Which is often called the goal-oriented communication also. And this only takes the relevant data. So here you can see the code what we have extracted, right? So that can be modeled in this particular piece of code. You can develop the entire library here, and you can say maybe you can apply self-attention based mechanism. Self-attention. You want to see what it does in the self-attention? I'll show you. This is self-attention transformer, right? So here, this is the root paper. So attention, all you need. This is the root paper, which you can take a look. Some of the people, they have a question. They have a question that what am I talking about the attention? See, this is the widely used paper which has been used by all these large language models. This is the pioneer paper, right? Whatever we are using, ChatGPT, GPT. See, GPT is generative pre-trained transformer, right? Chat is just like chat. GPT is common across all. So GPT is common across chat, GPT, Claude. Maybe they have their own transformers. Now, advanced transformers, Claude. Now what you call Gemini. Right? That domain. This was the pioneer paper here. Using this, people have started working on this and then they have developed further. So here you can see this is the pioneer paper. You can take a look. This is really a good paper. This paper has itself 50,000 plus citations. I think now it could have been 1 lakh. I'm not sure, but 50,000 last time when I checked. This is the architecture, the transformer architecture. Here you can see the input information comes here. It does the embeddings, then positional encoding to ensure that which word comes at which position. Then you have multi-head attention. There is a whole block, right? So here there is a whole detailed field. Then you have a neural network here. Then you have a feed-forward neural network here. This is not a neural network. This is an add and normalization branch. Then you have feed-forward neural network here. Then you have an add normalization branch. This is to cut down the dimension. Okay, so otherwise processing headache will increase. And then what you can do, you keep doing it, and then you have finally feed-forward neural network here. Apply softmax and get the output. Right. So that this gives the semantics. So you give the input paragraph here. This is the self-attention block. Input you can give it here, and then output is the number of selected semantics. And that's how you get model, right? So that's how you get model. So, and then semantics, which indicates what is the goal behind the information. That's how we model also, because unnecessarily, if we just keep seeing these slides, we may not be able to understand. So I'm trying to go back and forth to ensure that we have a meaningful discussion. Right. So now see, goal-oriented communication, what it does, it specifically focuses on the major relevant data, which is entangled with that goal or intent. And then according to that, it optimizes the network performance. And the parameter what it assigns to them, right? And just transmits the relevant data, the major context behind this, major context behind that, right? So what is the, so it generally asks that what is the goal definition, right? What is to be accomplished? And the objective function, what is the objective? What do you want to maximize or minimize? You want to maximize the bandwidth, minimize the bandwidth consumption or energy consumption, right? Whatever you want to define, that you define here in the objective. Then I define the context, and then what is my problem definition that I define and move on. Now, how do I do this? Generally, the traditional wireless communication papers, if you see that, what they do is they have some sort of objective function. What they define, so this is called the objective function, right? So they'll define the objective function, such as they say minimize the energy and bandwidth consumption. So that would be focused here as a function as under certain constraints. So you can say, let's say my maximum transmitted energy should be less than or equals to, let's say, the transmitted maximum power, or you can say E max, whatever my chip has the maximum rating, right? So I have to stay within that. And then let's say quality of service, QoS, must be less than or equals to, let's say, some sort of, let's say 2 dB. Right, so max, or you can say greater than or equals to, not less than or equals to. This doesn't fit here. It should be greater than or equals to. I'll just change it because QoS should be greater than or equals to some minimum requirement, right? Greater than 2 dB. Just an example. So those are the constraints. So we have to define the constraints here and then design the optimization problem and then solve it and then find the solution and then find the solution, right? And then that solution has to be deployed. That solution has to be deployed. Once you find out, you can put that in the code what we have defined, and then you can do. Now, how it does? See, let's say you have, how do you select? Let's say after that self-attention model, what we have discussed, you have multiple semantics you have selected, right? And you have multiple delays combination, energy bandwidth combination, and then different things, right? So virtually you can select, okay, I'll select this particular path and transmit, or I'll select this particular path and transmit, and then move on, and then move on. And it detects the failure also, whether you're transmitting or successfully or not transmitting successfully. There are certain applications of my semantic communication, such as, let's say, AR, VR application is really good. Defense related applications are really good. High data rate video transmission application, holographic communication. There are n number of applications are available here. All right. And that's what we have for a day. I'm a faculty member at IIT Dharwad, and I have multiple PhD positions open, MTech positions open. So we have, let's say, PhD and MTech research. PhD admissions, we do it every June and every December. You can apply if people are interested in doing the PhD. We have MTech research, MTech two type of MTech regular comes through GATE. A little bit of higher score is needed, and there is another MTech called MTech research, which is analogous to MS research, where you need a little bit of lower GATE score, just the GATE passing, right? Lower GATE score. So you can motivate students to apply for these two MTech programs. Apart from that, I have postdoc positions also. If someone is interested in this particular field, please feel free to apply, right? That's all we have for a day. Thank you very much for your time and invitation to present the thoughts here. If there are questions, please let me know. If someone wants to go through this video, I have already recorded this particular session. You can take a look. I've dropped the link there. Or if your students are looking for some sort of tutorials, you can share that link to that. Back to you. I'm open for all the questions and answers.
Participants are welcome to raise any questions or seek clarification.
Sugamano. No one is speaking.
Take, sir.
Yeah, go ahead. Go ahead.
Someone is asking question.
Okay. I am not able to hear the voice. If you can hear the voice, you can repeat. Attendance link, please. The question is attendance link in chat box.
Okay, thank you, sir. Actually, I am Dr. Prajul, Associate Professor in Department of Electronics and Communication in Jyoti Engineering College. My question is, what do you think is the most important breakthrough needed for semantic communication to become a practical part of future 6G network?
Mainly this hardware implementation is the critical challenge, hardware implementation. Specifically the chips to extract the semantics, right? And then run at terahertz frequencies and run at, let's say, what you call sub-terahertz frequencies also, let's say 140 gigahertz or something like that. Otherwise, the rest of the things are pretty much easy to create the codes and deploy. The hardware is the major challenge. Coding part can be done very easily these days. It's not a challenge. The manufacturing of the hardware is the major challenge. It's not just for semantic communication, it's for just entire terahertz communication, because we need the front end hardware at terahertz frequency. Then we need all the chips which we should be executing, and then the entire hardware, the up converters, down converters. Correct? So they have that everything, because the natural language processing models, they are rich. Large language models, they are rich. Coding part is easy. The only bottleneck is hardware. Good question, sir. Thank you very much for asking.
Is there any other questions? Participants can ask questions.
You're welcome,
Okay.
sir.
Thank you, Dr. Pandya, sir, for your
Thank you very much, ma'am.
valuable presence here. Thank you all the participants. This concludes day 1. Thank you. Thank you very much, sir.
See you. Bye-bye. Thank you very much for your time. I've dropped the video link. Please share with your students if they want to do some meaningful work. We can have a discussion with your students also. Thank you. Bye-bye.
Thank you, sir. Thank you, sir.